Maybe I start by thanking the organizers for all the work they did. And I owe you an apology because my voice is not very good. I hope that it will last for the duration of the discussion. Otherwise, we'll just quit and we'll have coffee. It's a bit strange, possibly, to have somebody who is founder and organizing committee member of the conference to be also a speaker. It's not my fault, believe me. This was an idea of my good friend Pavel, and I thought that it might not be too embarrassing as long as I keep my voice low, so maybe at least this part of it has been granted. I would like to talk about names and the way that we have developed for classifying things, which may at first look like unrelated subjects, but historically, if you look into the matter a little bit further, they are very tightly related. For one thing, during the Middle Ages, the inability to give names in a consistent way created serious problems. For example, here are two different names for the same thing, for a rose, a briar rose for that matter. According to one Middle-aged botanist, the briar rose was a Rosa sylvestris synodora seu caninem. And the other guy thought that the very same object would be instead the Rosa sylvestris alba cum rubore and folio glabro, which are both, more or less accurate descriptions of the organoleptic composition of these roses. But they made them unable to communicate with each other and to establish when was it that they were talking about the same thing. In fact, this confusion has been alimented through the years. I bet all of you in this room know this notion of a rose by any other name would still smell as good, by Romeo and Juliet. And much later, Gertrude Stein came up with this aphorism that a rose is a rose is a rose, which originally was not what she meant. She meant to compliment some friend of hers by saying that rose was the proper name of a person, was a rose, a rose, a rose. But then some erudite people, they came up with the notion that, wow, this is beautiful, a rose is a rose is a rose. So Gertrude Stein became famous for a quote that was never meant to be. And if you allow me to just inject a very little Italian thing, in the Promessi Sposi, the promised fiancés, which is possibly one of the most famous fictions, historical fictions by Alessandro Manzoni, at the beginning, he says that he will not openly tell about the names of the characters in his tale, because everybody will agree that names are only puri purissimi accidenti, which means something that is purely accidental, but have no meaning. Actually, it turns out that for the purposes of classification and systematization of things, names are very important. So by now we know very well, or do we, that King Philip came over for green soup. I'll probably explain for the two of you that maybe do not know what this means towards the end of the discussion. This acquisition is mostly due to the genius of Linnaeus. And in his Systema Naturae, Linnaeus systematized what he could see of the organisms that were macroscopically visible at this time. Many think that Systema Naturae was important for the classification that he did, and in my humble view, the most important contribution of Linnaeus was methodological. What he introduced in his work was the notion of binomial classification, which means the following. It means that he would take one and only one feature and classify objects based on this feature. So if we look at the classification, in this case, for example, you see that he takes animals and divides them into vertebrates and invertebrates. Then he takes the vertebrates and he classifies them into fish and mammals and so on. So there's only one feature that he takes at the backbone of his classification. And there is no overstating, in my view, of how important this intuition was. It took quite a few years before somebody could give an explanation of mathematical flavor about this thing. And this was done by somebody who thought perhaps about, the so-called Chinese taxonomy, which proposed that animals can be divided into those that belong to the emperor, the embalmed ones, those that are trained, the suckling pigs, mermaids, fabulous ones, stray dogs, those that are included in this classification, which is a nice evocation of the Russell's paradox, which gave rise to the theory of types. And those that tremble as if they were mad, the innumerable ones, those drowned with a very fine camel's hairbrush, the others, and so on, until those that resemble flies from afar, by which any jumbo jet would be basically part of this classification. Now, nobody actually ever came up with this classification. It was one of the many ways in which Jorge Luis Borges took fun, or in some sense, poked into the inherent contradictions of scientific method. This is taken from the Chinese encyclopedia entitled The Celestial Emporium of Benevolent Knowledge, that was attributed by Dr. Franz Kuhn by Jorge Luis Borges. Anyway, this would be, without the intuition of Linnaeus, just one more good, possibility of classifying things. And many years later, we got somebody who gave some mathematical substance to this apparent contradiction. There was a book written about 35 or maybe 40 years ago by a physicist of Japan by the name of Satoshi Watanabe, who wrote a beautiful book called Knowing and Guessing. I really encourage everybody to just browse through this book if you have a chance. There may be copies in libraries even today. And he stipulated a theorem. He was personally fond of Karun-Lev expansion, because in this expansion you can basically self-extract the most important features from a set of features. And his theorem says that as long as you do not have prejudice, you cannot classify. And he proved this by showing that, of course, you cannot measure similarity by the number of shared features, because by this measure, if you have somebody who is only the left eye, then he would be not similar to somebody who was the right eye, than somebody who has no eye. So this cannot be. And he said instead that you must measure similarity by the number of shared predicates. But the number of shared predicates can be computed. I will not spend too much time on this. But it is the same, it's exactly the same, no matter which two objects you take from a collection of objects. So biologists used to group organisms by morphology based on Linnaeus' method. And this went on and on for several years until we got this big news that actually phylogeny is also involved. It's not only, in other words, the way things look that are precise over the classification. It's always also the way that things have evolved. So by now we talk about classification that reflects phylogeny, and the kind of evolutional taxonomy that we accept today is evolutionary in essence. And this is what we mean by Linnaeus taxonomy nowadays. This is one of the renditions from the book that Charles Darwin set up himself. This is a more elaborate description of the same thing given by an enthusiast of Darwin's work, Ernst Haeckel, in The Evolution of Man. This is one thing by which I try to impress my friend Ami Amir, showing off that, tree of life sometimes is something completely different. In this case, the so-called Sephirot, various paths to perfection, which he has achieved, and I'm still trying to achieve. Anyway, so King Philip came over for green soup is a mnemonics for remembering the kingdom, phylum, class, order, family, genus, species, the ways in which we subdivide the living, or at least part of it. Over the years, we have evolved new ways to look into the various components of evolution. And there's been one big breakthrough that is predicated over the fact that if you have two programs that take similar inputs and give similar outputs, then this program must be similar too. This intuition was at the basis of the effort that we set up to sequence DNA and base taxonomy on DNA. There are many prominent figures in this effort. I will not even try to mention all of them. But of course, Linus Pauling is one of the pillars of this construction, and also one of the very few people who got the Nobel Prize twice, although the second time around he got it for different reasons than biochemistry. And then, of course, Margaret Dayhoff, which built the first protein database. And because we are in Russia, even if we didn't were in Russia, we could not forget, Vladimir Levenstein, who was doing something completely different. He was looking at binary codes capable of correcting errors. But because the errors that the secretary did, because now no secretary types anymore, we do it, and the errors that we find in genes and the errors that we find in transmission, they are all basically originating from the same mechanism. So Levenstein distance was basically taken to be the basic mechanism of alteration that would preside over the evolution at the molecular level. Maybe there are people in this room who still remember the way that at the beginning the kind of distances that were computed according to Levenstein were implemented. This is a PDP-8, which I am old enough to remember, and to still have nightmares about at night, because those little things that you see here, those little switches that you see here, these are actually, this is the console. This is how you programmed this little devil. You had to switch on and off each of those little switches. Maybe there are people in the room that remember this. This was a Dagstuhl conference that we organized together with Vladi and the late Rudi Ashvede back in 86. I can see some people, and some of them were from Russia. Anyway, sequencing has been speeding up at very rapid pace over the years, beginning with 65 and then the acceleration imposed by Sanger and Gilbert, and so on. Until now we have next generation sequencing, and we are still accelerating, we are still going on. So the point of my talk is that fortunately, over the so many years, we have accumulated ways to speak maybe more or less consistently from a methodological point of view about names and classifications thereof. And we have now many, many genomes and metagenomes, etc., that pose incredible problems. Some of them are very daunting, and they also impose perhaps a change in the game, in the sense that at the beginning we had problems that were of algorithmic nature in a straightforward classical way. And now, all of a sudden, we have problems that perhaps are of a different nature, but they are algorithmic nevertheless. And this is what I would like to highlight. They are of a different nature because they hinge on a factor of scale more than on sophisticated mechanisms of algorithmic construction. Let me try to recover a little bit of voice. So from the standpoint of applications, there is a big difference between the time of the origins and current times, in the sense that we have now way much more applications, and the interest of most of them is that they have to do more and more with clinical applications, with practices that are of medical nature. And so we have a chance to help with health, which is not a secondary thing of a secondary importance. So we have all these trees of life now that are being set up. And in a recent paper appearing in Genome Biology, Bonner and others, they also brought down where, according to them, the work will go. And I'm not sure that I agree with everything they said, but some of the things that they said are undisputable, particularly the fact that, of course, we will have a lot to do with in the domain of interpretation, and we will have a lot to do in the domains of analysis and so forth. But from my point of view, we still will have a lot to do in an effort to overcome the problems that are brought about by the sheer quantity of data that we are accumulating. So let me try to save some time here. I'm not sure I can. Okay. So for those two people that do not know what mapping what mapping is about. So of course sequencing is the problem of getting these little fragments of DNA, and once you get them, they are relatively short, more or less short, depending on the technology, pieces of fragments of a genome, or some fragment of a genome of various lengths, but these are relatively modest lengths. And then once you get them, you would like to match them against perhaps a known genome, which was not the case of de novo assembly, but where you don't even have a reference genome. At any rate, the problem becomes one of having all these little pieces and you want to match them against a larger piece. So the typical values of the so-called reads, that are these little pieces, little fragments, is m of them and the length of L, and you want to retrieve the matching positions. And there are a number of ways in which this can be done, for example, by suffix trees or hashing and so forth. One of the problems with this is that the matchings are not exact in real life. They are approximate, and approximate matches are much more complicated to find than normal matches. In fact, one of the holy grails of combinatorial pattern matching would be to find a way similar to suffix trees, that is to find inverted indices that could efficiently find lossy matches or lossy versions of inverted indices such as suffix trees. In a first approximation, the exact assembly problem would be a walk on what we might consider as a De Bruijn graph, where you hop from one node of the graph to the next based on the suffix-prefix superposition of these reads. But the classical problem at the intersection of pattern matching and genomics is, one way or the other, this iterated comparison of one string with the other. So we could say you have R strings of total length n, and for every pair of these strings, you want to find the best matches between a prefix of the first and the suffix of the second. We will see that this is also the very same basic problem that arises in metagenomics. In the simplest form, the best match is the exact match. But, and there are, good solutions to this problem, perhaps beginning with Gasfield, Landau, and Shiver in '92. And this problem is still being studied. But as Toby Berger pointed out in a paper that was written in the anniversary issue of the IEEE transactions on information theory, on the anniversary of the 48th paper of Claude Shannon. He said that perhaps as a consequence of the fact that approximate matches abound, whereas exact matches do not. It's more complicated to find exact matches than to find approximate matches than to find exact matches. In the CPM, we know that the barrier to this is the fact that in exact matching, we have the property of transitivity, whereas if A is equal to B and B is equal to C, then A is equal to C. But this property is broken when we bring about approximate matching. So there are also works that introduce errors, and they can be partitioned into least random. For example, I believe the approach of Kesesioglu and Jean Myers and Landau, Myers, and Schmidt. Other approaches are called overlap, layout consensus, filter methods, and there are approaches that are hybrid. Okay, let's forget this. From my point of view, one of the biggest places where work will go is data reduction. Many years back, talking about 97 or so, there was perhaps a handful of short genomes that had been sequenced. And at that time, the NSF and the European agency, they set up a meeting. They thought that it would be possible to let the American and Europeans collaborate. They didn't know, that there are different sociologists at work. Anyway, they set up this meeting. They took a number of us, like 30 people or so, and they organized this meeting in Annapolis. And the purpose of the meeting was for each specialty to tell how much work, how much resources, etc. they needed. And there were, of course, high-energy physics who said, we need a lot of money. And astronomers, they said, we have satellites pouring images all the time, so we need a lot of money. And okay, this is gravitational people that look at things upside down. Remote sensing. I had been invited to this meeting, perhaps because of my amphibious nature, and because they thought that I could represent the needs in bioinformatics. So at the time, as I said, we had hardly a couple of genomes. And I said, look, even the human genome is 3 gigabytes. I cannot even pretend to compare this with the... But I said, I can promise you this much, that we will mess up the biological molecular databases. We will produce so much of it that the atoms in the universe will not be enough to store everything that we will churn out. And I thought this was a joke, but it turned out to be very close to reality. So this is the problem that we face today with data reduction. And I believe it's one of the most serious that we face. So in this one, we see the relationship between Moore's law, so the rate at which we develop more and more powerful storage systems and the cost of sequencing. And you can see that the moral of the story is that the rate of production of genomes is going to outpace our ability to build devices and memory capable of storing these things. So ultimately, I'm going back. So that ultimately the question is, well, we will be able to generate more and more sequence based at a fixed cost. We will soon lack the facilities to store, process, analyze, and maintain the data that we generate. This is a very serious problem that will require very radical changes. For example, we have plenty of very efficient methods to compress data. Burroughs Wheeler, Lempel-Sieve, etc. None of these methods will be able to scratch the surface of this problem. Now, in certain situations, like, for example, in individual genomics, one could say, well, we don't need to sequence my genome every time I have a sneeze, or every time you need to sample again. You can just sample it once, and then annotate, perhaps, every time something changes, annotate the changes. But we also have, in each one of us, we have metagenomes, for example, guts metagenomes, that are probably of the order of magnitude of the complete system of Linnaeus. And what do you do with those? You cannot say, I will sample them every time I need them. Going back to taxonomy and the traditional sequencing, traditional sequence comparison, such as string editing, and etc., does not longer work in a situation where you need to compare genomes. So we have different gene orders, different genome lengths, lateral gene transfers, etc. All of these things make the systems based on, say, Ladi-Levenstein distance inadequate. And so one will need completely different systems. One of the most successful nowadays systems is the system based on so-called compositional approaches. Compositional approaches are based on the same principle as the so-called bag of words in information retrieval, except there is no words for genomes. So in the case of genomes, the words are, say, simple k-mers. And in this case, the natural question is, what should be the ideal K? Well, they found out that the ideal K seems to be somewhere between K equals 6, K equals 7, by which you can obtain very accurate kind of classifications. When it comes to metagenomes, the problem, though, computationally, becomes very demanding. To give you an idea of the situation, imagine that you have several gigabytes of reads or short segments. So we are talking about several gigabytes. And they come from one metagenome. So this is a soup of which you do not know who is in there. Maybe thousands of organisms. And then you have another soup. And you don't know who is in there either. And this is one more gigabytes. For each fragment in this soup, you would like to go and pick up the fragments in the other soup and compare one by one who is similar to the other one. So just if you wanted to know who is identical, you have the square of billions of little fragments. This is gazillions of comparisons. But you want to compare these gazillions approximately, and you want to compare them for each pair, you want to compare them sliding one of the reads or contigs against the other. These are incredibly large sets of things. So how to do this, how to compare genomes, etc., on this scale is something that I believe are at the same time one of the most demanding problems that we will face in the near future. And because of its radical, innovative features and flavor, it is, in my view, one of the most worthwhile tasks among those that this community can entertain. So I will stop here because my voice is at the end of the rope, and I'll be happy to discuss this in future occasions. Thank you.
Questions? While you're thinking about your question, Alberto, I wanted to ask you a question. So imagine the time when everybody in this room has a... Imagine the time when everybody in this room has a genome sequence, but then also goes every month to a clinic to sequence the immune repertoire for disease prevention, which will be 10 to the power 12 antibodies. And then already today, modern genomics is mainly about sublinear algorithms. Anything that is quadratic is just out of the question. No? So what are the new algorithmic problems? They should be sublinear. Do you see already what this community will be working on when it will unavoidably happen?
Yeah, I can sense, at least from direct experience, the limited direct experience that I'm having nowadays, that one of the problems I believe transcends to some extent our community, because as you hinted, it hinges on statistics. We will have to have very sophisticated sampling approaches by which, or they will have to have, because I'm not sure this is our job, to extract certain samples that matter. And then we would have to work on these samples. But with this said, there is this important, in my view, trade-off, that the bigger the sample, the better we will be able to come up with credible results. So it will be a game probably of team, in the sense that we will have to work together, hands in hands, with statisticians. They will have to understand more and more what we are doing. We will have to understand more and more what they are doing. But the bottleneck that I see is, as I try to point out, that this seems to be like a lost cause. Because I could not run too much, but let me see if I, some of the things that we are experiencing now, I will leave all of these on the web for those that yeah, this is, for example, a recent paper on classifying by just taking the correlation of, by correlation I mean just the superposition where they agree, with two proteomes. And these measures are very rough, they are very coarse. Nevertheless, they give relatively good approximations to the classification. For example, this is mitochondrial DNA. But the paradox is that in order to gain these relatively superficial measures, you have to do more work, not less work. And so it takes more work to compute less information. This is also, I cannot go into details now, but this is also one of the problems that we will face. That as we try to come up to pin down what is relevant, we might expose ourselves to more rather than less work. So I see problems everywhere. And what I'm trying to convey to you is that they may look like they're desperate, but with the appropriate alliance with the appropriate people, and this is people in biology and people in statistics, in my view, they may represent for this community a very interesting way to work. I don't have the answer, basically, to, these are problems in here, you see, this is a problem central to metagenomics, and also whether you have a reference genome or not. This is the problem that I quoted. So before we go this far, let me finish with what I had in mind to finish with.
Are there any other questions? If there are no questions, let's thank the speaker again.
Thank you.